In this video, we are going to discuss about Wee's theory of ferromagnetism and domain theory, hysteresis loss, and soft hard magnetic materials. Okay, now discuss about Wee's theory of ferromagnetism. What is the domain theory? Wee's proposed a domain theory to explain ferromagnetism. So, according to this theory, a single crystal of ferromagnetic material consists of a large number of small regions, and each region is spontaneously magnetized to saturation extent called a domain. Okay, and repeat it again. A single crystal of ferromagnetic material consists of a large number of small regions called as domains. Each region is spontaneously magnetized to saturation extent called domain. So the domain size may vary from 10 power minus 6 to the entire volume of the crystal. In each domain, spontaneous magnetization is due to parallel alignment of all magnetic dipoles. Okay, so the spin magnetic moment of all the atoms in a domain are oriented in a particular directions according to the domain. So the magnetization directions of different domains are random, so that the resultant magnetization of the material is zero or nearly zero in the absence of an external magnetic field. A ferromagnetic material magnetizes when an external magnetic field is applied. So the individual domains contribute to the total magnetization of the material. So when external field is applied, there are two possible ways of alignment of random domain, that is two process by which magnetization of the specimen takes place. That is, the domains randomly aligned and the domains aligned with external field whenever the field is applied. See the variation in the diagrams. Okay. Now, how the domain theory will be? By the motion of domain wall and by rotation of domain wall. Okay, so the domains that are parallel or nearly parallel to the direction of applied magnetic field will grow in size that of other domains which are unfavorable. That means here the motion of domain walls, the domain walls will change its direction along with the field. In the concept of rotation of domain wall, when the magnetic field is strong, the magnetic moments of the domains can rotate in the direction of applied field. Okay, now what is happening here? The magnetic moments of domains can rotate in the field direction, applied field direction. Okay, and now by the applied magnetic field, they either domain wall moments or rotation of domain magnetic moments or both takes place depending on the strength of the applied magnetic field. I am repeating it again. Whenever the field strength, it depends upon the field strength, that is either domain wall moments or rotation of domains in the magnetic moments possible, that is due to the strength of the field only. Okay, see, if a weak magnetic field is applied on a ferromagnetic material, then the domains of the material whose magnetic moments are parallel or nearly parallel to the direction of applied field will expand in size, whereas the domains in which magnetic moments are unfavorably oriented to the applied field will diminish in the size. Okay, what's happening? Whenever we are applying the field, the domains magnetic moments, okay, the magnetic moments present in the domain which are parallel or nearly parallel to the direction of the field, they will occupy the maximum portion and the remaining unfavorably oriented domains will be diminished in the size. See what's happening in the figure and B, A and B. Okay, and now this change produces a large magnetization for a bulk material, and finally by happening this, the domains that are set into the field direction. Okay, domain alignment, okay, in the figure B, and domain rotation due to strong fields. The complete domain will rotate. And finally the saturation due to very high fields. Okay, and next, hysteresis curve. This is also known as a BH curve. Okay, the hysteresis means lagging of an effect behind the cause of the effect. The hysteresis of ferromagnetic material refers to the lagging of magnetization behind the magnetizing field. Okay, the only hysteresis concept rises due to the ferromagnetic material, because what's happening here? The lagging of the magnetization behind the magnetizing field. What is the theory? Okay, that is the explained by the hysteresis curve. When the temperature of ferromagnetic substance, that is less than ferromagnetic Curie's temperature, the substance exhibits hysteresis. Okay, I am repeat it again. When the temperature of ferromagnetic substance is less than the ferromagnetic Curie's temperature, the substance exhibits hysteresis. Okay, the concept of hysteresis will rise. Now, the increase in the value of the resultant magnetic moment of the specimen under the action of the field applied, that can be attributed to two conditions, that is due to the motion of domain walls and rotation of domains, as we are studied in the Wies theory, Wies domain theory. Okay, just observe the diagram. What are the terms, what's happening here? See, from A to B, B to C, C to D, F. What is happening here? Saturation occurs in the opposite direction. Okay, at point A, B, that is maximum, that is we are exhibiting 2 here. There is a flux density B and the magnetizing force H. Okay, so at point A the saturation will start, and it is a B is maximum here, and at point B there is a term retentivity. Okay, and next at point C there is a coercivity according to the magnetizing force. At point F the field is a negative, and point E, what's happening? There is also a flux density, that is a negative, and at point D there is a magnetizing force. Let us see what are all those. Okay, what's happening here? What's happening here? Whenever it is in an unmagnetized state, okay, reversible domain wall moment, and next irreversible domain wall moment, change in magnetization direction, and finally it is in saturation state. Let us see what is that. Consider an unmagnetized ferromagnetic material. When a weak magnetic field is applied, the domains that are aligned parallel to the field and in the easy direction of magnetization grow in the size and the expense of less favorable oriented ones. Okay, next, this results domain wall moment and the magnetization of specimen increased from 0 to higher values. When the weak field is removed, the domains reverse back to their original state. Whenever the field becomes stronger, the domain wall moment continues and it is mostly irreversible moment. Okay, and next, the phenomena of hysteresis is due to this irreversibility. The concept of hysteresis rises due to this irreversibility of domain walls whenever the field is stronger. Okay, so application of still higher fields rotates the domains into the field direction. The magnetization increases rapidly with H. Once the domain rotation is complete, the specimen is said to be saturated. On removal of field, the specimen tends to attain the original configuration by the movement of domain walls. That means whenever we are applying the field, every time they are maintaining the rotation of domains in the field direction and finally get saturation state. Once we are removing the field of specimen, it tends to attain the original position by the movement of domain walls again. So, but this movement is hampered by impurities, lattice imperfections, etc. That is, the boundaries do not go back into their original position on reducing H, because in this here the H is reduced to 0. M does not decreases. Even it is 0, the M doesn't decreases in phase but lags behind H. Okay, now the value of magnetization that remains in the material even in the absence of the field is known as a residual or remnant magnetization. Okay, because even in the removing of the field, it is not regain its original position. Okay, it's maintaining some magnetization. The value of magnetization that is remains in the material even in the absence of the field, which is known as a residual or remnant magnetization. Okay, and next, to remove this field, the residual magnetism in the, that means the residual magnetism in the material, magnetic field is applied in the opposite direction, which is known as coercive field. That is the term represented by the coercivity. Okay, this is the lagging. Now the amount of energy spent in this regard is a loss. Okay, to regain its original position, we are applying the field in opposite direction. So the amount of energy spent in this is a loss. So this is a hysteresis loss, is the loss of energy in taking a ferromagnetic body through a complete cycle of magnetization, and this loss is represented by the area enclosed by the hysteresis loop. Okay, simply this is about hysteresis curve. Okay, in general what's happening means, whenever we are taking a ferromagnetic material, we are applying the field continuously to it. Suppose if there is 100 domains, 99 domains are set into the field direction, but the remaining one term it doesn't. So to regain its original position, to move that domain from that place to its original position, we are spending a extra amount of energy. That is regarding to the loss, hysteresis loss here. Okay, the curve represents the hysteresis loss. So it is traced, it is obtained, it is known as a hysteresis loop only. Okay, and next let us see what is the soft and hard magnetic materials. Okay, okay, based on the hysteresis loop area, magnetic materials can be classified into hard and soft magnetic materials. Let us see what are those. Okay, soft and hard magnetic materials. Soft magnetic materials have low hysteresis loss due to small hysteresis loop area, and hard magnetic materials have large hysteresis loss due to large hysteresis loop area, and that means the amount of energy required is depend upon the loop of the area. And these materials, the domain wall movement is relatively easier. Even for small changes in the magnetic field, magnetizing field, the magnetization changes by large amounts. But in case of hard magnetic materials, in these materials, the domain wall movement is difficult because of the presence of impurities and crystal imperfections, and it is irreversible in nature. Okay, see the difference between hard and soft magnetic materials. Okay, next, the coercivity and retentivity are small, hence these materials can be easily magnetized and demagnetized. The coercivity and retentivity is large, hence these materials can't be easily magnetized and demagnetized. So these materials have large values of permeability and susceptibility, and permeability susceptibility values are small for hard magnetic materials. Since these materials are free from irregularities, the magnetostatic energy is very small, which we are spending. In these materials, because of the presence of impurities and crystal imperfections, the mechanical strain is more, hence its magnetostatic energy is large. So they are used to make electromagnets. Soft magnetic materials are used to make electromagnets, and the hard magnetic materials are used to make permanent magnets, which possess permanent magnetic dipole moment. Okay, and see some of examples for soft magnetic materials and hard magnetic materials. Examples: iron silicon alloys, ferrous nickel alloy, ferrites and garnets are examples for soft magnetic materials. And iron nickel aluminum alloys with cobalt, copper nickel iron alloys, copper nickel cobalt alloys. So those are examples for hard magnetic materials. What is the use of soft magnetic material? What is the application? Mainly used in electromagnetic machinery, transformer cores, switching circuits, microwave isolators, and matrix storage of computers. We are using this soft magnetic materials. And hard magnetic materials for production of permanent magnets used in magnetic detectors, microphones, flux meters, voltage regulators, damping devices, and magnetic separators. Okay, so simply this is about the soft and magnetic materials, hard magnetic materials.